Good morning, ladies. This is Miss Leona speaking. As I've mentioned last week, I will be accompanying my advisory class to their immersion. So I will not be around today and tomorrow. But rest assured, I will leave you some activities so that your learning will not be compromised. So I hope everyone will pay attention to this discussion. I will try my best to explain the concepts clearly. And should you have any questions, please feel free to ask any of the science teachers. Or if you're feeling uncomfortable with them, you can ask your classmates to help you out. All right, so for today, we will be discussing the last gas law that we will cover, and that is the Gay-Lussac's law. So before we try to discover the properties of gases that are involved in this gas law and what kind of relationship exists between them, well, let's first get to know a little bit about the scientist who formulated Gay-Lussac's law. So his name is Joseph Louis Gay-Lussac. He's a French chemist and physicist, and he's known for his contribution and work on alcohol-water mixtures. But what is he particularly well known for? He's well known for his discovery that water is made up of two parts, hydrogen, and one part, oxygen. So if you can recall, water's chemical symbol is H2O, right? So that chemical formula is actually based on Gay-Lussac's discovery of water's element components, which are, as we've mentioned, hydrogen, and oxygen. Okay, so moving on to the gas law, Gay-Lussac's law aims to describe the relationship between pressure and temperature. So these are the two properties of gases that are being related by Gay-Lussac. So according to him, there is a direct linear relationship between these two properties, given that we are looking at a sample of gas with constant volume. So you have to take note that for Gay-Lussac's law, we are relating pressure and temperature together. However, we have to keep volume constant. Now, this relationship, this direct linear relationship, means that if we increase temperature, we are also actually increasing pressure, or vice versa. If the temperature decreases, then the pressure decreases as well. Okay? So obviously, the graph would be similar to the graph of Charles' law. So it's a diagonal line that is moving upwards. So this gas law, this Gay-Lussac's gas law, or relationship between pressure and temperature, is best observed in pressure cookers. I'm sure you're familiar with pressure cookers. I'm sure you have, well, at least most of you would have these at home. So pressure cookers are used for cooking meat or other meals. So in pressure cookers, as you increase the temperature, the pressure increases as well. So this helps the food to cook faster and make the meat more tender. Okay? So now to look at Gay-Lussac's law mathematically, we will write it as P is directly proportional to T, or pressure is directly proportional to temperature. Now to incorporate the constant, of course, we will write the equation as pressure is equivalent to constant times temperature, or P equals KT. Now, to rearrange this to get constant, we will write it as K equals pressure divided by temperature, or P divided by T. And as usual, of course, we have to establish the relationship further. So we have to compare two samples of gases. That is, again, constant volume. Okay, so we can say that K1, or constant 1, is equivalent to pressure 1 divided by temperature 1. That is for one sample of gas. And K2, or constant 2, is equivalent to pressure 2 divided by temperature 2 for a second sample of gas. Now, since K is constant, meaning it does not change, we can say that K1 is also equivalent to K2. So they're equal to each other. Now, to substitute K1 and K2, we will get pressure 1 divided by temperature 1 is equivalent to pressure 2 divided by temperature 2. So we have P1 over T1 equals P2 over T2. Now, if you're not comfortable with this form of equation, we can still rearrange it to come up with an easier formula to work on. So we will have pressure 1 times temperature 2 is equivalent to pressure 2 times temperature 1, or P1 T2 equals P2 T1. So these two are our formula or equations for Gay-Lussac's law. Now, let's apply the equation or relationship of pressure and temperature to problems. So, let's have practice problem number 1. So, 10.0 liters of a gas is found to exert 97.0 kilopascal at 25.0 degrees Celsius. What would be the required temperature in Celsius to change the pressure to standard pressure? So, first, we have to identify, as usual, our given. So, what are our given quantities or values? So, we have here pressure 1, which is 97.0 kilopascal. Temperature 1, which is 25.0 degrees Celsius. And that's it. No other numerical given. However, if we try to understand the problem, it says there, obviously, our unknown would be the temperature. So we're actually lacking the pressure 2. But it said there that standard pressure is used. So standard pressure would be 1 atmosphere. Please take note of this, that when we say standard pressure, it means 1 atmosphere. So we have our given already. Okay. Now, for our unknown, as I've mentioned, we are looking for T2, or temperature 2. Okay. Now, before we go to the solving, let's look back at our given. So, take note that the pressure is given in kilopascal, meaning you have to convert. So, for our conversion, we have 97.0 kilopascal times the conversion factor. So we know that 1 atmosphere is equivalent to 101.325 Pascal. But we can also say that 1 atmosphere is equivalent to 101.325 kilopascal. So we just move the decimal point 3 times to the left. Okay? So let's cancel the values of kPa. So 97 times 1, that's 97. And 97 divided by 101.325. We will come up with 0.957. So let's round off to 2 decimal places. We have 0.96 atm. Next, we have to convert our temperature first into Kelvin. So it's easy to do that. From Celsius to Kelvin, we just have to add 273.15 Kelvin. So 25 plus 273.15, that will be 298.15 Kelvin. Okay, so now we're done with our conversion. We can now solve. So for the solution, let's rewrite the formula first. So P1 T2 equals P2 T1. Now we're looking for T2, so we divide both sides by P1, giving us T2 equals temperature 2 equals pressure times temperature 1 divided by pressure 1. So to substitute, pressure 2 is 1 atmosphere, temperature 1 is 298.15, divided by pressure 1, which is 0.96 atmospheres. So let's perform the operation. 1 times 298.15 Kelvin, that's 298.15, divided by 0.96. So temperature 2 now is 310.57 Kelvin. So that is our answer for T2. Okay? You may copy the problem, you may copy the solution. I'll give you 5 minutes to answer practice problem number 2. So what is the new pressure in atmospheres when a constant volume of a gas is heated from 25.1 degrees Celsius to 37.5 degrees Celsius? The starting pressure is 755 mmHg, or millimeters of mercury. So take note that you have to convert both of the temperature into Kelvin and pressure into atmosphere first.